Welcome. Today we're going to discuss the epsilon-delta definition of the limit. And the limit definition says, for each epsilon greater than 0, there is a delta greater than 0, such that if x minus c is greater than 0 and less than delta, which really says x is no further than delta units away from c, and of course is not equal to c, then f of x minus L is less than epsilon. In loose terms, as x gets close to c, f of x gets close to L. Okay, so let's look at what this means. First, we always start with, let's choose a positive epsilon. So let epsilon be greater than 0. Okay. Now, let's look at our, what I would like to call our scratch pad. The formal proof will be done over here, but we do need to do some legwork, our scratch work over here to figure out what's going on. So let's first look at, what is this expression, f of x minus L? Well, we know what L is. L is 10. We know what f of x is, or f is. That's 3x plus 7. So let's see. This would be 3x plus 7 minus 10, which is equal to 3x minus 3, which is equal to, factoring, 3 times the quantity, absolute value of x minus 1. All right. Now, that's simple algebra. What happens, and we want this to be less than epsilon, as stated in the definition. Well, let's look and see what happens. If that were less than epsilon, then we could divide both sides by 3, and we could deduce that x minus 1 is less than epsilon over 3. And now let's see. This is, by the way, now when we look at this expression, we see this is, c is equal to 1 here. So this is the x minus c, the absolute value of x minus c part of the definition. So what we see, or we can imagine, is that this looks like this might be a good choice of delta. Okay? So that's our candidate for delta, based on this scratch work. So let's move over here, and based on our scratch work, let's let delta equal epsilon over 3. Now obviously, since epsilon is positive, positive 3 is positive, positive divided by positive, delta is in fact positive as needed in the definition. So let's, now we need to consider this inequality. So suppose x is no further than delta units away from c, and of course suppose x is not equal to c. This is what we call the deleted interval. We could look at this on the real line in a moment, but let's suppose that, and by the way, remember the c is 1, that x is no further than delta away from 1. Again, delta is equal to epsilon over 3. So what we have is 0 is less than the absolute value of x minus 1 is less than epsilon over 3. Why? Because delta is equal to epsilon over 3. Okay? So now let's do some work. Let's look at some algebra. Again, it's roughly going to be the same algebra that we had in our scratch pad, but in reverse, so to speak. So let's multiply both sides by 3, or all sides of the inequality by 3. Now remember, 3 is positive, so when you multiply both sides of an inequality by 3, and 3 being positive, you leave the inequalities alone. So 3 times 0 is 0. 3 times the absolute value of x minus 1 is just precisely that. And 3 times epsilon over 3 is, of course, epsilon. Okay. Continuing, let's bring the 3 in. 3x minus 3 is less than epsilon. And 2 more steps and then we're home. This is equal to 3x plus 7. Negative 3 is equal to 7 minus 10. So 3x minus 3 is equal to 3x plus 7 minus 10. And finally, we realize this is f of x, and the 10 is L, so we've done it. We've shown that if x is no further than delta away from 1, then we don't really care about this. This is a kind of a bonus result. This is what we care about. Then we've shown that f of x minus L is less than epsilon. Certainly in this case it would also be positive. Therefore, by the epsilon delta definition of the limit, we have shown the limit as x approaches 1 of 3x plus 7 is in fact 10.